as was mentioned, my name is Brian Kinross. I'm going to be presenting today on iMFLUX and the development of software with Moldex 3D to create a simulation option or package or feature to simulate an iMFLUX process. So I'd like to start out a little bit with with an introduction to iMFLUX and who we are, what we do. Some of you may have been exposed to iMFLUX, but I would like to give a company overview just so you understand how iMFLUX technology offers a different solution to molding. What we like to call it is molding on the green curve. So just a little bit about iMFLUX so you understand how it's molding, how we're molding differently, and why a simulation module that simulates the iMFLUX process would be useful to users like yourselves. So our company is very innovative. We are, our iMFLUX is a compilation of innovators that are transforming the future of plastics injection molding. We're a subsidiary of a wholly owned subsidiary of Procter & Gamble. So we're created by P&G. We're trusted by companies around the world. And what is it that we do? We divide our offerings into a couple different categories. One is that we develop software and controls technology, which is what I'll be focusing on today, and really focusing on simulating the resultant of that software and controls technology. And then we integrate that software and controls into a molding machine, and it changes plastic flow. Changes the way plastic flows through the mold and the way the part fills. So what is our product? It's pretty simple. We don't make machines, but we do make them run smarter. We equip an existing machine. We can retrofit existing machines, and we can also we're also working with OEM partners like Cincinnati Millicron to deliver ready machines that are ready with iMFLUX on board that contain all the elements to have an iMFLUX software option readily available on the controller. But the key components are a pressure sensor in the nozzle, our software, which again is either retrofitted add-on as a separate control box, or it's integrated into a machine at the build stage. And then there's also a user interface, which again is either a separate HMI or it could be embedded within the OEM HMI. So what is it that is different about iMFLUX? Let's study what I want to show here is we're going to look at molding from a perspective of melt pressure. And if we look at what we call the blue curve, which is the melt pressure curve plotted of a conventional process, this is a stereotypical plot of what a conventional process looks like, where we're modeling the filling phase, which is that phase in which melt pressure achieves a peak pressure. The packing phase where the pressure is dropped and maintained constant, and of course the cooling phase, which is the time it takes to cool the part. So this is the industry standard. It is a multi-phase process where you have filling phase controlled by velocity. Pack and hold phase is controlled by pressure and time. The qualification process is fairly complex. It's a decoupled approach where you have the machine operating in a velocity controlled mode and then transferring to a pressure and time controlled mode. And then the operator touches are frequent because we see the process is very static in that material variation. The process is established with a specific material, and if there's any variation, it could require operator intervention to accommodate those changes. With the iMFLUX, we refer to our pressure plot, our melt pressure plot, as the green curve. And the key characteristics is that it is a constant pressure process where there is no phase change from a velocity controlled phase to a pressure and time controlled phase. It's pressure and time throughout the entire process. In doing this, the technology that iMFLUX has developed offers a real closed loop molding solution. It's adaptive, it's autonomous in nature, provides shot-to-shot consistency that is highly repeatable with less variation than what conventional process will offer. And then we can also offer meaningful sustainability solutions where materials with wide spec resins, wide spec MFI can be processed using iMFLUX, and we've had great success with customers that are molding in that environment where the resins they have are extremely wide spec. So some of the benefits are that there's lower pressure, combination of fill, pack, and hold into a single phase, which actually ends up yielding a faster cycle time, and which is a result of the combination of the phases, which require less time than a conventional fill or decoupled tube process with filling and pack and hold as two separate phases. And then cooling time is also usually there's usually a reduction in cooling time that offers contributes to the reduction in cycle time. So with iMFLUX, this is kind of an animated view that shows the melt pressure transducer receiving information as the part is being molded. The transducer is located in the nozzle area. We actually create a custom built adapter that screws into the end cap of the injection unit, and then the nozzle, which we initially remove, attaches to that adapter, attaches back to the adapter. And so that adapter is the housing for the sensor. And while the part is molding, as resistance changes within the mold, the key goal of the software is to maintain pressure at a constant. And so as features within the mold, like corners, changes in geometry, pinch points, or where you have a thick to thin to thick, like we're showing here, will all change the pressure that's detected at the sensor location. And so velocity is profiled for these changes in geometry that are detected while the plastic is flowing through the mold. So this creates a very adaptive, nature where we can adapt in real time as we're detecting changes in resistance. There's no sensors required in the mold, and we can run with any mold, any material, any machine, and the ability to adapt gives the user flexibility and the benefits of less operator intervention. So this is the other. I mentioned this earlier, but this is a diagram just to show the difference in the velocity profile of iMFLUX. While iMFLUX fills slower, you can see the filling pattern of this. This is a cap for a Mr. Clean bottle, and you can see that with conventional process, the filling pattern is very fast. With iMFLUX, the filling pattern is slower, but that doesn't mean lower constant velocity to achieve that slower fill. With iMFLUX, the velocity response is a variable velocity that is used to adjusted to maintain pressure at the set point established. Whereas with the conventional process, the methodology is a constant velocity during the filling phase. And so that variable velocity fills the part slower, but creates a different fill pattern that has benefits that result in reduction in stress, cycle time reduction, reduction in sinks, warp, and shrinkage. The process, as we mold at constant pressure and monitor the filling pattern, we can and close the loop on the filling pattern. We created a very adaptive molding process, similar to self-driving cars. The feature that enables molding wide spec materials, or accommodating for lot-to-lot variations, or even accommodating for small MFI shifts within a narrow spec material. We call this auto viscosity adjust. And as you mold at constant pressure, the changes in viscosity will affect the filling pattern or time to the end of fill. So the iMFLUX system monitors that filling pattern, that time to end of fill, and as changes occur, for example, a lower viscosity material, this is simulating a shift from a higher viscosity to a lower viscosity material. So as that resistance is reduced, less pressure is required to fill the part. The filling pattern is tracked by the iMFLUX software, and viscosity changes are detected, and in this case, it's detected that the viscosity is being reduced, and therefore the driving pressure required to fill the part is adapting autonomously and automatically being reduced to compensate for the lower pressure required to fill this lower viscosity change that's happening within this process. So again, this could represent a lot-to-lot change. It could represent a wide spec resin that has a lot of variation, or it could just represent, you would see smaller, tiny changes even within a tighter spec material. But the key here is that it's autonomous, it adapts, and it continues to make quality parts. So yield improvements and lower, less operator intervention is the resultant here. So the other area of iMFLUX business is mold making, and when combined with when we look at a project and initiate a project from design, early design stages, having the ability to simulate iMFLUX and detect benefits that the process can offer enables us to design the molds with iMFLUX in mind, and realize benefits that in the mold build and the product and the mold design that can have very positive benefits to OEE and to profitability of the users. So examples are the opportunity for higher cavitation molds because we mold with lower pressure, lower clamp tonnage is required. The opportunity to upcavitate is there. Up to 50% tonnage reductions could enable the user to decide to run the mold in a smaller press as long as the mold course fits within the tie bars. And then you could also realize the faster cycle times, smaller gate and runner sizes, or even fewer drops into the part. So all these can be, so we call this Nexus, our Nexus molds, because it's a connection or a combination of features that provide a benefit to the user. And this is an example of a Nexus project where the product was a Swiffer ball end joint for a Swiffer handle for the Swiffer sweeper. It's a P&G product, and using that approach of simulation and determining benefits in the early design stages of the mold, iMFLUX was able to realize a 50% upcavitation, going from an 8-cavity mold that was at the time running in China to a 12-cavity mold, and actually putting that in a smaller tonnage press, going from a 500-ton to a 400-ton press. As you can see, there's the corners of the mold are a little notched out to drop and rotate it into that smaller footprint. 37% cycle time reduction was achieved. Overall throughput was 191% when you combine those two benefits. And then while we're able to reduce the press size to a 400 ton, and spec that out for the new facility that was molding these parts in the Dominican Republic, the actual clamp tonnage that's utilized to mold this part is only 300 tons. And then iMFLUX has the ability to do complete turnkey systems. We have a molding innovation and education center that has space for customer molding machines to drop in and develop tooling and develop process, and then deliver the whole package of the machine mold to the facility once completed. So that's iMFLUX. That's kind of the introduction to who we are. So now, hopefully there's a little understanding that iMFLUX is different, and there is a need for simulating the iMFLUX process in the industry. The benefits that could be realized are having the iMFLUX simulation as a predictive tool to determine iMFLUX benefits in the early stages of development, to determine what process settings would be used for initial process setup at your site, looking at opportunities for designing the product differently due to the nature that iMFLUX offers, or the way that iMFLUX fills the part, which could result in thin walling and lightweighting your part, changing runner geometries, or even looking at different materials that currently may not be moldable with the conventional process, which is actually a very common occurrence, that we're able to mold materials that are challenging for conventional molding today. And then with the benefit to our mold manufacturing is gating definition, size, location, quantity. Those would all be, that having the simulation would enable, of the iMFLUX process would enable us to define very accurately these gating definitions. And then the productivity analysis of opportunities for upcavitation, press tonnage requirements, where we could reduce press size requirements based on the simulation results with the iMFLUX of the iMFLUX process. So because of that, we've have been working on a project since would have been February of 2020 with Moldex 3D to develop an iMFLUX simulation module. And I'm going to lead you through the development and kind of update you on where we are with the in our phases of development. So just to look at the plan that we're taking, it's a 3-phase approach. Phase 1 is completed, and I'll share the studies there. Phase 2 is underway and is well within its objectives. And then phase 3, of course, is to be completed after phase 2. So to start off with our phase 1 development, we started by taking an existing product, which is the Mr. Clean flip top cap pouring spout, and did I molded parts with the mold that produces this cap, and then provided data to Moldex 3D to correlate actual and simulated results, and to ensure that we had a good correlation between the Moldex 3D technique for simulating iMFLUX and the actual iMFLUX process. So these are just setups. I'm going to blow through this quickly for interest of time. Material is PP. This is the modeling exactly the drop design for that particular part, location. We also modeled the sensor location at the end of fill. And then this is how to set up an iMFLUX process, basically. So the tool that Moldex is creating is a range finding tool. The objective is to determine at what constant pressure is required. The minimum constant pressure is required to fill the part, so you complete the 100% filling of the part. So this is also instructive for those who want to, before module's released, there's also opportunities if you want to do a pseudo simulation of an influx process. Looking at the settings here would help guide you. So they're setting up the melt temperature, mold temperature, same as the actual experimental runs that I did in our lab. Fill by volume with the influx process. You basically skip you want to skip the inject phase and jump right into the hold phase. And so that's how you set up your simulation module. And so that's why you can see volume switch over volume is very small. So basically switching over right at the very beginning of the process into the hold phase. These are the you want to set the machine to its maximum pressure, so it allows the software, the Moldex software, to study all pressure range from 0 to its maximum. And then these are just other setups, again, by you want to set a filling time very small, transfer by volume very tiny, so that it switches out of the filling velocity controlled stage, basically right into the packing. Set the packing time long, and then have the packing pressure refer to the machine pressure. And then your set the injection speed to 100%, injection pressure profile set to 100% of machine capability, and packing pressure set to 100% as well. So this is how you set up, how you would condition or set up the settings on Moldex 3D to run an influx simulation. The software developed runs iterations and runs through different pressures. And what it's trying to do is create a process window, and really what we're going to demonstrate here is really just finding this lower end of the process window where you find the lowest pressure required to fill this part, the lowest constant pressure required to fill this part. So this is the actual process window that I discovered in running this part in our IEC, our Innovation and Education Center. And what I found is that the low pressure required to fill the part was 8750. The high pressure was 1100 psi, or 11,000 psi. And then you can see there's a center point there. So I provided this data to Moldex, and then the idea is to run this module that finds that window and then compare that back to actual to see how accurate the results are. So in this case, the simulation indicates that the lowest pressure is 8,500 psi. So within the ballpark, definitely a good result. Here, what this is looking at is the lowest fill time. So when we do our range finding with influx, we'll find the lowest pressure and then the low and high times that correlate with those low and high pressure settings. And so this is the simulation results show that the low fill time at 8750 was 2.5. The results of the actual experimental data that I ran show that it was 2.4 seconds. So you can see at the high pressure, 0.7, 0.9. So the times are in line. Good correlation between actual and physical results. Same thing with the part weight, where the Moldex 3D predicts a little bit higher part weight, 0.3 to 0.32 grams higher. So the correlation, though, is a good, really good correlation. It's a one-to-one correlation when you look at the trend through the data. And so there's just we see a slight offset that the prediction is calculating the weight a little bit higher, but the slopes of the trend lines are the same for both the experimental data and the Moldex 3D. So we find that see that as a good encouraging result. So just summarize these results is that the polyline set point, or I'm sorry, to continue the simulation results, we went on to examine and create a polyline, which is basically a representation of the set point line the actual results, and then run those actual results to see the correlation between melt pressure, cavity pressure. So this is going outside of just finding that pressure range. This is actually studying the response of cavity pressure, melt pressure throughout the entire process, the flow front comparison, the shrinkage between influx and conventional stress analysis, and then the part weight comparison. So that's what these next slides do. This screen here shows the pressure plot, and it's a little hard to see, but it's this green curve here that is the pressure plot of the influx process at the low pressure and at the high pressure settings. And so Susan, who did the study at Moldex, created a polyline to basically mimic the same profile, and then of the high pressure and the low pressure, and then runs the simulation to see if the simulated results for those items that I previously, the list that I previously went through, are how similar those are to the actual. And so we'll show you the results here. So this represents the big red dot is where your material enters the part. End of fill sensor location is shown here, and that matches, correlates with the actual. And so these are the results. The blue curve that's shown here is the influx results, the results that were run in our lab that I ran, and then the red is the Moldex's prediction for melt pressure at the high and the low pressure settings. So you can see that we have very good correlation. There's a slight shift in the in this end of fill response, but we'll address that here, where you can see that the cavity pressure, as we overlay the actual cavity pressure response from the experimental data to the Moldex simulated cavity pressure response, there's a slight offset in the initiation of the cavity pressure response going greater than 0. But where the system develops end of fill pressure is actually very, very closely correlated, and is a good result. The influx system, just to understand the reason for this, is that in our influx system, it is designed to respond to an in-cavity sensor if the user has those installed in their molds, and this the change in cavity pressure will result in typically a lowering of melt pressure to finish the filling of the part at a lower constant pressure. And the purpose of that is to keep the stress of the part low, to continue to fill the last 2% of the part under a lower pressure conditions, to avoid flash and to avoid inducing too much stress in the part. So the influx system is autonomous in its reaction and response to cavity pressure. So here, this is at the high pressure setting. Again, you can see very good correlation where the pressure is detected. The simulated versus actual has very good correlation in its response. So this is an overlay of the actual conventional process that I developed for this cap, which is the blue curve, and then the green curve here is the Moldex 3D simulated melt pressure for the conventional process, and then cavity pressure. You can see how the overlay is very good, almost 1-to-1 there. So, and then as you look at the opportunities, so as we study, okay, what's in it? What's the benefit for me as the molder? Well, here's one of the opportunities, and this is actually using the high pressure. So there's even more reduction that can be realized if you run to the midpoint or closer to lower pressure settings. But 37% reduction in peak melt pressure was seen to be an opportunity in the simulation of the two processes and comparing them to each other. Looking at your cavity pressure, this is kind of a view of what cavity pressure looks like, conventional versus influx. So you can see the pretty significant reduction in cavity pressure from 64 megapascal to 40 to close to 48. And you can see that in the parts where you have high pressure in the conventional process and much lower in the with the influx process. So this is showing that at end of fill cavity pressure comparison, again 16% reduction in cavity pressure is shown to be an opportunity in simulation. And just looking at the filling pattern, again, this is somewhat of a correlation thing. This is an actual, the photo on the right are actual parts, and on the left is the simulated results, just to show that the simulation is mimicking very well the actual fill pattern. And this is the influx fill pattern. But looking at volumetric shrink, what we find is that the conventional process is actually overpacking the parts, and that the influx is not. And this is influx at 8,500 psi, and influx at 1,100 psi. So the percentage of shrink is maintained at a low level. Residual stress. This is looking at conventional simulated results, influx simulated results, and then these are the actuals where you can see the lower level of stress in influx parts versus the higher level of stress in the conventional parts. And then part weight analysis, we find that there is a prediction of a 1% reduction in part weight using influx versus conventional. So these are the benefits in these are actual benefits. So there were some simulated benefits that we just reviewed, but the actual benefits realized on this project is a 41% reduction in melt pressure. The prediction was 38. 46% reduction in cavity pressure, 3% weight reduction, 8.75% cycle time reduction. And so having those numbers as a molder, looking at this and being able to have those numbers in front of you as a result of simulation and comparing influx to conventional results, it enables you to make some pretty key decisions. One opportunity would be, or look at a couple of key opportunities. One opportunity would be to investigate or to have the opportunity to upcavitate from maintain a tonnage of 750, which is what would be required for a 32 cavity mold and a conventional process. But the influx process enables you to upcavitate to 48 and still stay at the same tonnage because of the reductions in cavity pressure and melt pressure. And the other trade-off that could be realized is keeping the cavitation at 32, but reducing the press tonnage or the press size down to a 500-ton press. So these are opportunities that can be realized and evaluated and discovered having a simulation module, which is why we're continuing to work on this and to provide you as a users that opportunity to use it and to see what benefits could be realized. So now in phase 2, our key, this is just a single slide, I'm out of time, but shows what we're doing in phase 2 is that cavity pressure response is what we're adding, so that the simulation module will respond to the cavity pressure seen, and that would be a something that doesn't need to be polyline profiled like we did earlier, but that would be an actual response. So the way our system, quite simply, the way the influx system works is we use a factor, end of fill factor. Factor is unitless, so it's for example, if I used a factor of -1, that would mean that for every 1 psi increase in cavity pressure, I would have a reduction in melt pressure of 1 psi. In this case, you can see the factor is more like just trying like looks like about 30.3. So for every 1 psi increase in cavity pressure, I'm getting a 0.3 decrease in melt pressure. So that factor is something that is utilized again to create this lower pressure for the end of fill, and the purpose is reduction or maintain low stress and don't flash the part, and maintain, and also to provide the weight reduction that influx typically offers, which is usually 1 to 2% weight reduction. So Just conclusions, our next steps is that we finished phase 1 development. Correlation studies are completed. We have good confidence in the correlation of the Moldex software to simulate and accurately predict an influx process. The next steps, we're in phase 2, working on development. The goal is to complete that by May 1st. And then phase 3 is really just clean up the knobs and levers and make it look like an influx setup. And then prep it for release. And the target there is August 1st. So that's my presentation. If you want to learn more about influx, follow us on social media. There's good video segments on YouTube that provide instruction on influx demonstrations from shows that we've been to. So check us out. Look at follow us on Twitter and visit our website as well.